There has been quite some attempt to make GenICam useful for embedded, but to be honest, at that point in time, we were not really successful. And the reason for that is two technical challenges and one political one.
Welcome to a new episode of our inVISION podcast, 5 Questions 2. Our topics are image processing, machine and embedded vision, AI and metrology. My name is Peter Ebert, Editor-in-Chief of inVISION, and I'm happy to have you here for a new episode.
Welcome to another episode of our podcast. This time our topic will be 20 years GenICam. The goal of the GenICam standard, which is hosted by the EMVA, is to provide a generic programming interface for all kinds of devices, mainly cameras. No matter what interface technology people are using for their applications or what features they are implementing. This year, GenICam celebrates its anniversary, and inVISION invited Fritz, Dierk, Director R&D Systems at Basler, and Michael Schmidt, Senior Product Architect, also from Basler. Both have been active in the GenICam Technical Committee for years. Just listen how it all began, what has happened since, and what the future might hold. Hello, Fritz. Hello, Michael. Nice to have you here in our podcast.
Thanks for inviting us.
Thank you from my side as well.
It's a pleasure. Okay, let's start immediately with the first question. Could you briefly explain what challenge in machine vision inspired the development of GenICam 20 years ago and what the biggest hurdle was in the beginning?
Maybe I can say something too, because it's about history. GenICam was created when there was a discussion about using GigE as an interface for cameras, so creating the standard which later became GigE Vision. And we had two problems there. One was technical and one was political. The technical problem was that at that time it was common to use a fixed register layout for camera standards like IDC for 3094 Firewire cameras. And the problem is that this is extremely inflexible. So if you wanted to add a custom feature, you just couldn't. Or you could only use a void pointer, and this would mean that nobody who uses a standard driver could use your custom feature, and that was not so nice. And there was even a more severe problem with fixed register layouts because you couldn't change implementation. And the IDC, for example, had only 12 bits for exposure time. So if you wanted to have a dynamic range more than 1 to 4,000 for exposure time, you just couldn't. So nobody wanted to have a fixed register at that time. And then there was a political problem because when we sat together and asked ourselves which register layout to use, of course, all major companies fought for their own custom standard. Because everybody had their own house standard for register layout, and everybody wanted their standard to become this standard because then they would have an advantage and their product's already ready. So nobody wanted to agree on that. And the whole thing was more or less stuck. And at that point, I remember that we had a configuration tool for our cameras at Basler, which worked a way that you wouldn't fix the registers, but you had a configuration layer where you could design features by names, type, and meaning, and configure which registers you have to set and get in order to touch these features. And I propose that this might be a way out of the whole thing. So we don't agree on all the details of the register layout, but we standardize only names, types, and meanings, and standardize in XML format where you can put in the mapping between the features and the details of the camera. And this could be specific for every camera and every vendor. So everybody would be free to add their own register layout. And everybody was kind of relieved that there was a way out. But only if I had known how much work that would be in the past, I'm not sure I would have proposed that. But in the end, it worked out. And that's the birth of GenICam.
What was the biggest hurdle in the beginning?
I think it was making people agree on a totally different way of dealing with camera features, because everybody was aware how a fixed register layout worked, and now there was a completely new idea and people were a bit reluctant to adopt that. But I think we were in such a desperate situation because the market expected this GigE Vision standard to become live kind of 2006, and we were end of 2004. We just didn't have a clue how to get out of that. So everybody said, okay, give it a try. And it was even kind of worse because we had the GenAPI mechanism, which is the XML file, and the first round of standard the standard implementation ready on the Vision Fair in Stuttgart 2005. And then people said, oh yeah, and of course, then we now need a list of standard feature names and types. So do you have one? And of course, we didn't at that point because we were totally focused on getting the standard mechanism running. So we had an emergency meeting beginning of 2006 hosted by National Instruments in Austin. And within, I think, 1 week, we agreed on the basic set of the standard feature naming convention, which is still there today, fighting a bit about the names, but we were completely desperate. And we learned at that point that it's much easier to agree on names, types that is kind of, is it an integer, a float, or an enum, and meanings, but compared to kind of agreeing on bit depth and register stuff like that. So this was really the first time we realized what kind of speed you can gain if you adopt this GenICam idea. And we found that to be true later, because the way this grew over time was kind of that people typically made a custom feature for something new, which wasn't in the SFNC, and then showed up on the next meeting and said, hey, we have something, we know that it works because we have one customer who used that, and they just would propose the custom feature they have, and then we just adopted that for the standard, because a feature becoming standard just means it shows up in the SFNC. The implementation is the same.
Interesting. Next question. Standards are always great, but always means some kind of limitation on the other side. How does GenICam balance standardization with flexibility for manufacturers to offer their own unique features?
Well, as Fritz has just explained, most devices for machine vision applications like cameras have a rather simple register interface. And this was even more true 20 years ago, but hasn't really changed until today. I would like to compare the register interface to an assembly language. It's compact and efficient, but each processor model brings its own instruction set. Errors are easy to make and hard to find, obviously, and it's really a pain to work with. Today, we have high-level languages like C++ that allow you to describe your program in a processor-independent way. And the compiler translates your source code to machine code and takes care of many other things like type checking, for example. GenAPI is a bit like the compiler. It provides a convenient high-level programming interface and translates it to the low-level register interface nobody really wants to work with. When I say GenAPI, I mean the standardized XML description and the standard library. And to stay in the metaphor of compilers, you can write anything you like with a C++ compiler, but all programs that operate under a certain operating system like Linux or Windows must agree on the same interface to open a main window, for example. And for GenICam, this common agreement would be the SFNC that Fritz also mentioned, the standard features naming convention that defines how features for standard functions are named and how they work. And that makes it a lot easier to write software that works with devices from multiple vendors. So you can basically write one software that works with a Basler camera, but also with a competitor camera.
The camera from another vendor.
Right. But the device vendors can always choose to add features that are not standardized. And in principle, they can also choose to replace standard features with their own. Obviously, they cannot have the same names, but you're free to implement your own version of exposure time control if there's a need for it and if there's a value in it. And that's how we balance the flexibility with support for own unique features.
GenAP was the first GenICam module to be ratified in 2006. What are the main developments since then?
Maybe it's a bit history again. I can answer that. You need at least 3 modules in order to really cover the key things you need in order to deal with the camera. The one is the configuration mechanics, which is the GenAPI module. And the other is the standard feature naming convention. So you get standardized names for the features. But there is a third one, which is the GenTL, the transport layer driver access, because if you want to use drivers from third parties, you have to have a standardized way of dealing with them. The reason why this wasn't released in the beginning, it was mainly about GigiVision and 1394. And for those interfaces, the camera manufacturers used to have their own drivers. So the business needs for an interface dealing with drivers was not much there. And in addition, the standard group was just so overloaded that we didn't find the time to really finalize the GenTL module. And this was true even up to the advent of USB 3 Vision, which was also an interface where people used to do, the camera manufacturers used to do their own drivers. but it changed with the advent of CoreExpress, because CoreExpress is a frame grabber-based interface, and the frame grabbers used to come from different vendors than the camera. So with the advent of CoreExpress, there was a strong need to have a GenTL interface standardized, because otherwise people wouldn't have been able to combine the cameras from one party and frame grabbers from the other party. And that's the reason why GenTL was then added together with CoreExpress and was also made mandatory for that. But of course, there are more things which were created on the way. And maybe, Michael, you can comment on the other modules.
Yeah, sure. The most important ones are the PFNC, the Pixel Format Naming Convention. This standardizes the names and the formats of pixels. So if someone uses, for example, a Bayer red, green, 8-bit format, they know what data formatting they can expect. Another module that came up in the quite early days of GenICam was a CL protocol. That's a common protocol driver for camera link configuration interfaces. And that's also something necessary if you have a frame grabber, because the software has no idea how the frame grabber will provide the serial interface to the camera. Later came GenCP. GenCP is a standardized protocol for the control channel. And that was, for example, used in USB 3 Vision. And the idea is that you don't want to reinvent the wheel over and over again, but you do it once and then can use it for different transport layers. The latest addition was GenDC, which stands for Generic Data Container. And GenDC is a format to combine several image components in one container and provide a generic way to transport this container. Again, like GenCP, you invent the wheel once and use it multiple times. So you can apply the same format to a number of transport layers, which makes it much more efficient, for example, for 3D cameras.
A lot of modules, a lot of work. AI and embedded vision are playing an increasingly significant role in machine vision. How might these trends influence future GenICam developments?
I would like to begin with AI. AI often means neural networks and image processing, and those have been around for several years. AI processing is usually done on a host system, for example, in a GPU, and also some embedded systems provide accelerators that can be used. And these can be inside a machine vision camera, but don't have to. And even if they are, they typically act and feel like a regular Linux system with one or more cameras attached to it. So what we have here is a standard system that looks like a camera. So GenICam has all that's necessary to connect a camera to such a system. But Fritz, you are deeper into embedded systems than I am. Maybe you want to comment on the second part of the question.
Yeah, there has been quite some attempt to make GenICam useful for embedded. But to be honest, at that point in time, we were not really successful. And the reason for that is 2 technical challenges and 1 political one. The technical challenge is that embedded use is normally implemented based on Video for Linux, and people are used that functionality for cameras are implemented in kernel mode drivers. And GenICam is not really suitable to be run in kernel mode because it's quite a large thing and it needs to be run in user land. And the other challenge is that in the embedded world, people are used to program using GStreamer. And that is a different programming model than the model we've chosen for GenTL, where you get hand over every buffer and have to treat with it as compared to a streaming thing. So these are the 2 technical challenges. And the political challenge is most of embedded stuff is run under Linux. And the Linux community is very strongly insisting on software needs to be open source. And the GenICam reference implementation is currently not open source for a good reason, because we wanted to make sure that the reference implementation isn't forked. The reference implementation currently can be used by everybody, but you're not allowed to make a fork from that. And the reason for that is if you test against the reference implementation, and this is something every software vendor is using, then you can get away with a way lower testing effort than if you needed to get the GenICam implementations from every software vendors, because every software vendor may have done their own fork and you have to test and test and test. And the same argument goes the other way around. if you're a software vendor and you want to test with a camera, you can rely on, if you do the camera with the reference implementation, you have to test only once as compared if the camera vendor started to make their own fork. So this is a reason why GenICam is not open source, but the Linux community kind of hates it and doesn't adopt it. Of course, there are approaches to solve that. The approach to solve the kernel mode problem is typically that you do the GenICam reference or run the GenICam reference as, implementation as a daemon in userland. And if the kernel mode gets kind of a call set, let's say gain to 10, then you just switch to userland and ask the daemon what kind of register you have to set. And then you can set it from kernel mode. And we have tried, there's prototypes from that works pretty well. And as for GStreamer, this problem can also be solved. And there are several implementations around already where you can just make a GStreamer pipeline and put in the pipeline something like gain -10, which means you want to set the gain to 10, and you can just seamlessly put that into the GStreamer syntax. And under the hood, it's done by GenICam. So that can also be solved. We just didn't solve it at the time when we first tried to do the whole thing embedded. And as of the open source, IMVA, which is governing the GenICam standard, is currently discussing whether to make the reference implementation open source, so that problem will maybe also go away.
Interesting to know. Now we have looked at the past. Now we would like to look at the future. Looking 10 years ahead, how do you expect GenICam to evolve by 2036? Who likes to be the first looking at the future?
Well, one major extension we are already working on is a standardized feature interface API. The working title GenFea, but it will not keep this name probably. The current Gen API defines the format of the XML description, but the standard library, the reference implementation to interpret the XML file is technically not a standard, and it has many more functions than are needed just for feature access. And our idea is now to specify exactly the functions an application needs to enable different and potentially simpler implementations. And if all works out well, this will allow us to bring devices under the GenICam umbrella that could not be integrated so far. For example, devices where you don't have an XML description, but instead have an API like webcam, for example. Another possible extension for the next 10 years are the convolutional neural networks that we already discussed. Should they gain more traction, there might be a need to standardize the way the networks are configured. But to be honest, at the moment, I can't see a clear trend towards this, but we may be surprised.
We're looking at the future, so all is possible and all can change.
When I prepared this interview, I thought a bit about what may be next. And I think we all agree that today's disruptive technology is clearly AI. And if you look at the way software interfaces are made today, you see that AI is changing things quite drastically. And if you look in the very old days, you typically had a telnet access for a piece of software. So you sent a carriage return in, and then you got a kind of small menu back. So press 1 for this, press 2 for that. So it's the very old days. Today, the standard is have a GUI interface. So everything you can do with a piece of software, you can see in the GUI, and you have tons and tons of menus and stuff. But the problem with that approach is that software is becoming so feature rich that the GUI is kind of too complex, and it's just too many features, and you cannot really deal with it anymore really good. And the next step, which is also be seen already to come, is that you just get a chat interface. So you get a little GUI to see the status, but in the end, you tell your software what you wanted to do, and then it just does it. And I think this is kind of the future of the interface of dealing with software. And I think something similar might also happen to the way cameras are configured. So in the old days, we had this fixed register layout. Today, it's the standard is GenICam. But even with GenICam, you have the problem that there are just too many features. For example, a couple of weeks ago, I had on an internal fair to deal with a system where there was a frame grabber and a co-express camera, and I wanted to install it and configure it. And there were so many features present that I just got lost. And that was the point where I said, oh, this is maybe not the way of doing it. And my vision here is that you typically get a kind of MCP style interface based on an SDK. So not on the camera, but on the SDK on top of that. And you just take your pet AI, you connect to the camera, and if the camera not only exposes the features, but also certain traits on how the image is, like a histogram, for example, you would just be able to tell the camera, well, can you please increase the contrast? This does look awful. And the camera will just look at the histogram, find out what to do, change it, and maybe even show you a live image, say, is that okay? And then you're done. We have done prototypes for that, and I know others have that too. And I think this is the future of how to configure cameras, and maybe some of these ideas even make it to the GenICam standard one day.
If I may interrupt here, I believe we already built an interface ready for modern AI 20 years ago. Just 2 examples for it. The SFNC works great as an input to large language models like ChatGPT, because it's a full description of a collection of the common wisdom of the machine vision industry. So it's a perfect instruction how to use a machine vision camera. And also, at least when it's done well, the XML description can provide most of the necessary information for a model like ChatGPT to understand and use the custom features of a camera that are not in the SFNC, because the XML description also has documentation fields and things like units, for example, which are a good guide to configure and also to compose systems. And that said, I think that generative AI like ChatGPT or maybe image generators is nothing I see in machine vision devices like cameras, for example, or not in the interfaces in the foreseeable future. I think it will have its place when it comes to creating and optimizing machine vision systems. So I think a large language model should be able to propose the right components and tell you how to connect them and then write the application for it. That should all be possible. But I don't see it in the image processing loop because it's just too slow and too unpredictable for most applications. But for the users I mentioned, GenICam is already in a very good position. I think it has a good future in combination with AI systems. Other than that, I think that GenICam 10 years from now will look very similar to what we have today. The modern technology like AI will need factories that produce the components for it. And the factory will need more or less classic machine vision technology. And therefore, I believe that AI will not replace the existing machine vision components, but basically change the way we design with them.
So it seems we're coming to an end. First of all, I would like to say once again, happy birthday, GenICam. Thank you, Fritz. Thank you, Michael, for your time, for your answers, for your giving us insights into GenICam. And for all the people who would like to get more information about GenICam now, or would like also to say happy birthday to the standard at Vision Fair in Stuttgart from October 6 to 8. There will be the International Machine Vision Standard booth hosted by EMVA. So you have the chance to get more information about this standard, other machine vision standards. So people would be happy to give you there any more informations. And Fritz, Michael, I think it's time to say goodbye. Thank you very much and see you. Bye.
Thanks for having us. Bye-bye.
Bye-bye.
If you would like to find out more about inVISION, please register for our inVISION newsletter at invision-news.de/news, become a follower of our LinkedIn channel, inVISION News, or find out about our webinars at invision-news.com/Tech Talks. I look forward to welcoming you to our next episode of our inVISION podcast, 5 Questions 2.